A lot of these questions are going to look familiar, especially if you've been back and reviewed any of this stuff. What I want to do is use each one as a, notice there are none of them that are highlighted. I want to do every one in this document. And I want to use the questions where possible to as a jumping off point. In other words, just change the parameters, get you think about how the answers could change. Okay. All right, so let's start with some of them. It's going to be hard to do that because they're just definitional. Which of the following is an example of a quantitative observation? We know the difference between the quantitative and the qualitative observation. I think numbers. Right? If you got numbers, it's quantitative. If you don't have numbers, it's qualitative. And that holds for every example I can think of. A piece of metal is longer than a piece of wood. There's no numbers there. It's just a comparison. That's qualitative. Solution 1 is much darker than 2, qualitative. Liquid beaker A is blue. That's not a comparison, but it's not numbers either. Temperature of the liquid is 60 degrees. That's it. That's quantitative when you've got numbers. All right. This ought to erase pretty good until I rub off all the WD-40. Which of the following has a different value on the moon compared to Earth? Well, let's see. What kind of measurements can we make? We could make mass. We can measure weight. We can measure length or volume. A host of others. Let's see, what else are we given? We're given moles also. Moles. Time. Right? Do any of those change on the moon? What's different? Gravity. Right? Moon has less gravity. It's not going to affect time. The only place time is affected is close to a black hole. Moles are just the counting numbers of things. That's not going to change. Volume won't change, neither will length. Mass won't change either. Mass is constant. Again, as long as you're not near a black hole or traveling close to the speed of light, then mass changes. But for our purposes, the only one that really talks to a difference between the two heavenly bodies is weight, because mass is a measure of substance. How much is there? Weight is a measure of force, right? How hard am I pressing down on the surface of the earth because of the size of the earth? That's the main difference between mass and weight. Is it just me or is it hot in here? Just me. That's what I get for taking prednisone. Let's see, number 3. All the following are characteristics of non-metals, except. Okay, when we talk about metals and non-metals, metals are almost all solids at room temperature. We have one liquid at room temperature, mercury. We have a couple that are really close, like gallium. If you put gallium in your hand, it'll melt. But at room temperature, they're almost all solids, whereas nonmetals can be solids, liquids, and gases. Metals, they're malleable. Let's see, is that 2 L's? I think it's 2 L's. Malleable, ductile. What is ductile? Malleable means you can bend it, shape it. Ductile means you can stretch it into a thin wire. Whereas nonmetals are brittle if they're solid. Brittle solids. Metals, if they're polished, will be shiny. And nonmetals are typically dull if they're solids. So let's see. Let's get back to the question. All the following are characteristic of nonmetals except, heat. Right? Heat conductor, non-conductor, and electricity conductor and non-conductor. Okay, so nonmetals, characteristics of nonmetals except. Nonmetals are poor conductors, that's true. They're brittle. If they're solid, they're brittle. They're not ductile, right? So C would be a good choice there. They have a dull appearance, tend to gain electrons in chemical reactions. The nonmetals are on the right-hand side of the table. And remember from our trends, periodic trends, the electronegativity increases as you move to the right. So as you get over into the nonmetals, they tend to accept electrons much more readily than the metals. Metals want to get rid of electrons, nonmetals want to accept electrons. So that's true also, nonmetals. They tend to gain electrons. All right, how about 4? The question here is to name this compound. So how do we name compounds? We have 3 types, right? Type 1, 2, and 3. 1 and 2 are metal, nonmetal. And type 3 are non-metal, nonmetal. So we got a metal and a nonmetal. It's one of these. And we have to tie break. The tiebreaker is whether or not the metal is capable of more than one charge. Because these are ionic. These are covalent. So remember, you only have a few in the periodic table that have fixed charges. Right? First column, all +1s. Second column, all +2s. Aluminum, gallium, indium, all +3s. And then there are 3 of them in the transition metals that have fixed charge. Silver, cadmium, and zinc. They have fixed charges. So iron is not among any of those. That means it has to be a type 2. So that means we have to know what the charge is on iron in order to name it correctly. So where do we start? Well, we start with oxygen. All the chalcogens, when the chalcogens are in ionic compounds, they're always 2- charge. Oxygen groups, they'd always be 2-. So that's where we start. That means iron has to be a +2. So we're going to say iron 2. Have to say the charge, oxide. Okay. Let's see. What if we had, no, I won't throw that one at you. I'll tell you what I was thinking. Fe3O4. If we start with -2 here, that's -8. Now, how do you get an even number out of 3 of these and +8? You don't. Because this is a composite. If you ever see this one, it's actually 2 different compounds, Fe2O3 and FeO in the crystal structure. And you would name them separately. You couldn't name this one correctly according to that because it doesn't have a whole number charge. All right. Number 5. The correct name for Ca 2 plus. Right. Well, we know it's calcium. But is that the end of the story? We know it's a calcium ion also. But do we have to say what the charge is? No. Calcium is an alkaline earth. It's a fixed charge. All we have to say is calcium ion, and we know it's unambiguous and it's not redundant. Unambiguous means we give it all the information you need, the minimum information you need to go from here to here or from here to here. And non-redundant is you don't give any extra information that's already there, right? If we said this, that's redundant. You don't need it. Calcium is always 2 plus as an ion. So calcium ion tells you everything you need to know. That's why the answer is B. You've probably seen this one before. I put this one in here because understanding symbology, right? We're making symbols here of atoms, individual objects, spheres, triangles, squares, they're individual atoms. So how they associate with one another goes into answering the questions. You'll notice that in A, all the atoms are very far apart. Right? That signifies a gas. And there are 2 types of atoms here. Right? We've got the one that's solid, grayed in, and one that's not. Then B, we've got all the same. So that's an element. And they're regularly arranged. That's a solid. C is another gas. Only this is a gas of a single compound. A combination of a small gray one and a large open circle. Then D, we have a mixture there. That's probably a liquid, right? It's not a regular structure, but it's not pure either. You've got a gray and a clear circle, right? So that would be a mixture. And doesn't seem to be regularly arranged. So I would think that it's probably heterogeneous. And then E, we have compound and element. The square is an element. All right, so now let's answer the questions. Which best represents a heterogeneous mixture of 2 elements? So let's find one that has 2 elements in it and see if it's a mixture. D has individual elements and they're not uniformly distributed. So I think that's probably the good choice for 6. That's a heterogeneous mixture of 2 elements. 7 is a homogeneous mixture of an element and a compound. All right, so let's find one with an element and a compound. And E looks like a good example. The squares are elements and the 2 circles hooked together is a compound. And they seem to be regularly arranged. All right, so E would be a good one for 7. What best represents a solid element? I would go straight to B. That's definitely a solid, and there's only 1 element in there. Is that it? Yeah, that's it for that. All right, so we can move on. Number 9. I didn't write those numbers up here. So the viewing audience will have to pay attention. All right. All the following are in aqueous solution, which is incorrectly named. Now we've got nomenclature for acids. Okay, H2SO4, H2CO3, H2SO4, H2CO3, and H3PO4, HCl, HCN, yeah. Okay, remember the rules for naming acids. These, we're already told, these were all in aqueous solution, so I don't have to write that up there. First thing, to recognize an acid, it starts with a hydrogen, at least one. It can have more hydrogens over here, like for instance, HC2H3O2, acetic acid. Okay. That's the hydrogen that's responsible for the acidic character. These hydrogens are locked in place. They're not going anywhere. So it's just that one hydrogen that we're interested in. So as long as you've got that first hydrogen available in the aqueous solution, then you look at the rules for naming. Is there an oxygen? If there's no oxygen, then you start the name with hydro. So let's go to this one, hydro. And then you look at this one. This would normally be named what? If it's a gas, it would be hydrogen chloride. So we say ides become X, hydrochloric acid. That's what that one should be. Is that D? Yeah, that one's correct. How about this one? We'll go ahead and do this one since we're here. Hydro cyanide ion. That's a polyatomic ion. You need to recognize polyatomics. Cyanide, I becomes ic. Hydrocyanic. So is that one correct? No, that's the bad one. Thanks. How about this one? It's got an oxygen in it, so we don't start with hydro. We look at this part right here. And invariably, if there's an oxygen in there, you're dealing with a polyatomic ion. So this is phosphate, and eights become ic. So we say phosphoric acid. This is carbonate ion, eights become X. Carbonic acid. And sulfate. Sulfuric acid. Now we don't have any in there that are, what if this were H2SO3? SO3 is ite, sulfite, and ites become us. So this would be sulfurous acid. Okay. Or you could have a series, right? You could have, let's see, ClO3, ClO4, ClO2, ClO, make an acid out of each one of them. This is the chlorate, so this would be chloric acid. This is perchlorate, this would be perchloric acid. This is chlorite, this would be chlorous acid. And this is hypochlorite, this would be hypochlorous acid. Okay. Now, while we're here, which one's stronger? The one with the most oxygens. Right? The more oxygens you have, the stronger the acid. So this would be the strongest one. Strength would increase that direction. You remember why? Because these oxygens are attached to that chlorine. Let's see. Oxygens and oxygen, like that. What happens, oxygen is so electronegative, it draws electron density away from the rest of the molecule. It draws it away from here and weakens that bond. And the weaker this bond, the more likely that hydrogen is to ionize and enter solution. So the more oxygens you have, the weaker that bond, stronger the acid. All right. All right. Now let's talk about accuracy and precision. Let's see. Okay, it's just the one. Just the one, number 10. Of those targets, which one represents low precision? Remember the difference between accuracy and precision. In order to assess accuracy, you either need a true value or an accepted value to compare. So if you have a true value, like a bullseye, then the closer you are to the bullseye, the more accurate you are with single shots. But if you're judging several shots together, then you take the average of them. And is the average close to the bullseye? Right? For precision, all you don't even need a bullseye. Precision, you just need the grouping, right? Is it a tight grouping? Or is it a wide open group to determine precision? So which one has the lowest, have low precision? That is the poorest precision. And I would say Roman numeral 1, right? There's a lot of scatter there. And if you average those together, it's not even going to be close to the bullseye. So number 1 is not just low precision, it's low accuracy. Now number 2 is high precision, low accuracy. And Roman numeral 3 is both high accuracy and high precision. Which one are we missing? Low precision, high accuracy. So that would be if you have a bullseye here, and you have one there, one there, one there, one there. The average of those would be right there. So that would be high accuracy, low precision. Okay, so the answer is A for that particular one. All right. Number 11, the amount of uncertainty in a measured quantity is determined. What determines the amount of accuracy in a measured quantity? Well, you got two things. Think of yourself, say you're in the lab and you're asked to do some measurement, whatever the case may be, right? What does that measure depend upon? Well, you're probably going to use some kind of instrument. I mean, even if it's a yardstick or a meter stick. But more than likely, you're using something a little more advanced. And when you make that measurement, the instrument has built into it an inherent inaccuracy, right? Because all measurements have some inaccuracy. All measurements, whether they're human or machine, they're all inaccurate to a certain extent, some more than others. And then, of course, there's the operator. If the operator has experience with the instrument over hundreds or thousands of operations, then they're probably better at making the instrument do its very best, right, and minimizing the error from the instrument itself. But if the operator is inexperienced, new on the job, and they're using an old instrument that's kind of cranky, right, which I can speak to that personally, then it's more difficult, whether you're a good operator or not, whether to get the value. So you've got two things to consider, the instrument and the operator, which would be C. When I first went to work for the USDA, we had this instrument called an inductively coupled argon plasma spectrometer. It sucked up your solution, had metals in it, and ran it through this hot torch that was inductively coupled to a fluctuating magnetic field, and it was argon gas was carrying it through there. And this instrument was several years old, and just every once in a while, it would just, for no reason, just stop working, right? And when I came on board, I talked to the other technicians and I said, "What do you do, you know, when that happens?" I said, "We shut it down and go away and do something else." We don't bother with it. So when they hired me to run the lab that it was a part of, it was my duty to try to figure out what was wrong with it. Eventually we did. Right? It was just one little electrical circuit in the power supply called a crowbar. And when it overheated, it separated and broke the circuit, right, to protect the instrument. So once we figured out, and I put an oscilloscope on it so we could catch it in the act. And then when the technician came to service the instrument, I said, look at here. He said, "I know what that is." So we fixed it. And from then on, it worked right. So, you know, instruments are not infallible. And let's see, we've done that one already. And sometimes it just takes persistence. All right. Which of the following are incorrectly paired? All right. So we've got the E. We've got that element. What is that? That's an alkaline earth. And I'm basing it on the choices, right? So where does it come from? Well, it's the second column that makes an alkaline earth. So V, where's vanadium? Vanadium's period 4, right? It's a transition metal or a transition element. Okay. Cl, that's a halogen, along with fluorine and bromine and iodine. And then H. H is an animal all to itself. The only reason we stick it over there on the left is for balance, right? It's not an alkali metal, right? And it's not a noble gas. It wouldn't sit next to helium because it's not a halogen. We just put it over there because there's no other place for it, right? But it's definitely not a noble gas. Hydrogen is just hydrogen. It's got its own little club. It's the only member of that club. Uranium, we look for uranium, right? It's down here. And these are all the actinides. Right, we call it actinide because where they start, right? There's actinium. That's where this whole row fits right in that slot right there. Once you get down to lawrencium, then you're off on Rutherfordium. Carry on. Right, so the one that was wrong was hydrogen. It's not a noble gas. Yeah. 13. The boiling of water is. Okay, let's look at the answers to find out what's they're looking for. Physical change, chemical change, all right. And then there's an explanation. So first of all, boiling water, is it a chemical or a physical change? Did the identity of water change? No, it just went from liquid to steam. So it's a physical change. Now we've got two possibilities, A and B are both physical change because what? Well, A says the water merely disappears. It doesn't disappear, right? Right? You can't do that to matter anyway. Matter doesn't disappear. It can change state. Yeah, it can do that. So the gaseous water is chemically the same as the liquid. That's absolutely true. So B would be your best answer. All right. Let's see, we got 14. Let's see, do I want to draw that table? Yeah, let me draw the table. So 1, 2, 3, 4, 5 across. Let's see, about right here. Here. And then how many down? We got 1, 2, 3, 4. So we got 4 for the, I'll put them up here, and then we need 3 down this way. Because I may want to put an extra row in there. Okay. This is what's given up to this point. Okay. In the first column, we got the symbol. And then we got the number of protons. Protons. Number of neutrons. Number of electrons. And charge. I'm watching a 3-part series. What is the guy's name? Al-Khalili. He's a theoretical physicist at some university in England. And his first episode was on the atom. He gave the historical build-up to how we discovered what the atom was and how it's made, and all more detail than I give you in my discussion. It's really interesting. And he even introduces personality conflicts. See, some of these scientists were really invested in their beliefs. And when a new guy comes along and says, well, I don't believe that, then you're going to get a controversy. Okay, so we're given 206 SN, given that one. We're given this one, plus, we're given this one, and we're given this one, and given this one, and we're given this one, and we're given this one. I think that's all that we're given. Okay, I'm going to use a different color for the rest of it. I'm going to regret it because they're harder to erase, but for clarity's sake. So how many protons do we have for this? Have to look it up because it's not given to us, right? 10, there's 50 protons, right? This is neutral, right? We know because there's no charge there. So that means we have the same number of electrons. And there's no charge. So how many neutrons do we have? 156 plus 50. 156 plus 50 is 206. Okay. How about this one? 35 protons. What's that symbol? Let's say 35. Bromine, right? Bromine. Is there a charge? Yeah, there's an extra electron. So it has a -1 charge, or 2 plus. Same difference. How about the mass number? 35 plus 40 is 75. Right? Okay, how about this one? Iron has how many protons? 26. It's got a 2 plus charge. That means it's got 2 extra protons more than electrons. That means the number of electrons would be 24. Right? In order to keep that a positive 2, we have 24 minus 26. Well, 26 minus 24 would be 2 plus. Okay. Is that everybody? That's everybody. How about what if, let's see, what if about
Now to get the neutrons for that, for 10, You could do the 206 minus the protons to give the 156.
That's exactly how you do it.
Okay, I was just making sure my thought process was right.
Yep.
So if they give us that number to figure out the neutrons, we can just subtract the protons.
Yes.
Okay.
And we found this number ourselves.
Yeah.
From periodic table.
Yeah.
Uh-huh.
Okay.
Yep.
And to get that number, you just add the neutrons and the protons if it's given.
Correct.
Okay.
Yep. That usually doesn't give students too much trouble. It's the net charge that bothers them.
Yeah.
Because you can't mess with the protons. You mess with the protons, you got a different element.
The protons always stay the same.
Right.
And that's what's on the tape.
Right.
Got it.
Yeah. Number of protons, symbol, they're joined at the hip.
Got it.
That's enough. Let's move on. 14. Ooh, that one came off good. Remember to use purple. Okay. Name some compounds. All right. 15 through 21. Nineteen, 20, 21. All right, 15 is CF4. Can you big mark? CF4, type 1, 2, or 3? 3. Non-metal, non-metal. So we borrow from type 1, type 2 convention, and we say carbon, but there's no charge to balance. So we have to say how many fluorines are. So we definitely have fluoride, but how many fluorides? 4. And we need the prefix. The Greek prefix for 4 is tetra. Carbon tetrafluoride. Okay. LiH. Okay. In this case, we have a non-metal and a metal, but we're gonna call it the metal comes first, so it's lithium. And what do you do with hydrogen? Hydride. Just say hydride. That's it. Now, if we had to say what the charge is, we look at lithium, which is an alkali metal, it's +1s. So hydrogen has to be a -1. Right? I think we covered that in the last chapter. Right? Those possibilities when we were trying to do oxidation states. Hydrogen in the covalent compounds is +1, but in this arrangement, hydrogen is -1. COI2. CO2. Metal, non-metal. Cobalt can vary. Right? It's not one of the fixed charge. So we have to say, all right, what is iodine? Well, in an ionic compound, iodine is like any halogen, it's a -1. So that means -2 is balanced by a +2. So that means we say cobalt 2 iodide. Okay. What about this one? Well, we got a metal and a non-metal, so it's either a 1 or a 2. In fact, it's a type 1 because silver is a fixed charge. So we only have to say silver chloride. Okay. How about HNO3 aqueous? Did one kind of like this, didn't we? This has got oxygen. This is an acid right there. There's your hydrogen. There's your polyatomic ion, which is nitrate. 8's become X. We don't say hydro, so we just say nitric acid. That's it. How about N2O5? Non-metal, non-metal. So it's a type 3. So we just say how many there are. We say di-nitrogen. Penta. Actually, we drop A. It's pentoxide. And the last one. NH4NO3. NH4NO3 can be used as either nitrogen fertilizer in your corn crop, or you can make a bomb out of it. You just need ammonium nitrate and 6% fuel oil, and then a stick of dynamite will help get it started. Then you can drop a whole building in where was it, Oklahoma City, Alfred P. Murrah building. That's what Timothy McVeigh and his conspirators did. They had these big barrels. They mixed up that ammonium nitrate and fuel oil, set it off in front of that building, and it just collapsed half the building. It was a big bang. Okay, so this is ammonium, right? When you have polyatomic ions, their names are fixed. So we just say ammonium and their charges. Ammonium nitrate. That's it. We're done. Now we're going to write formulas from the names. See if I've got any left for this. Okay, 22 through 27. That. All right, first one. Magnesium hydroxide. Well, let's see. Definitely got magnesium in there. What's hydroxide? It's a polyatomic ion. OH minus. This is a 2 plus. That's a 1 minus. And this is a type 1 compound. Alkaline earth is always 2 plus. And we need 2 negatives to balance that 2 positives. But polyatomic ions, we can't split them up. That negative doesn't belong to that hydrogen. It belongs to the whole group. So we have to use parentheses. Dibromine heptoxide. So we know we got bromine. We know we got oxygen. Non-metal, non-metal. We got 2 bromines and 7 oxygens. Hepta is 7. Then manganese 4 oxide. So we've got manganese with a 4 plus charge and oxygen with a 2 minus charge. So we need to balance those. Right? We need 2 times these 2 to make 4 minuses to balance. So MnO2 should be the correct formula. Sulfurous acid. Now, we know we're going to have hydrogen first. Sulfurous is derived from sulfite. Ites become us's. So the ite is SO3, 2 minus. That means we need 2 hydrogens. And if it's an acid, it's an aqueous solution. Now you don't have to leave the charges in there. That's just for bookkeeping purposes. Okay, next, acetic acid. Acetate, right? It has oxygen in it, obviously. It's going to have the acetate polyatomic ion, which is a -1. That means we only need 1 hydrogen to balance it. Right? So HC2H3O2 is acetic acid. Oops. in aqueous solution. Nitrous acid. Okay. It starts with hydrogen. But what polyatomic is it? Us's are derived from ites. So NO2 minus, we only need one hydrogen. HNO2. Like that. Okay. And moving along. Let's see. 28. The manometer. What's a manometer? It's a meter that measures man. No. It's a modification of the barometer to measure the pressure of an entrained gas. So manometer is attached to a sample of gas that occupies a volume of 2.34 liters. So we got this sample of gas. See, like that. 2.34 liters of that gas. And it's attached to a manometer, where the mercury level in the arm of the manometer attached to the gas sample is 24.3 torr lower than that of the arm open to the atmosphere. So do like this. Okay, here's our manometer. This. All right, we got mercury in there. And it says that the mercury in this side is lower than it is in this side. So we got mercury over here. We got mercury over here. And the difference between those two is 24.3 torr, which is the same as millimeters of mercury. Okay. But we also have atmospheric pressure there. So is the pressure inside greater than or less than atmospheric? Greater than, because it's pushing here enough to lift that much mercury up in addition to the atmospheric pressure. So the total pressure inside, is that the question? Atmospheric pressure is measured at 1.23 atmospheres. Oh my goodness. It's kind of high. And the answer is given in torr. So we have to convert this to torr. How do you do that? Oops. Atmosphere. Atmosphere converted to torr. 1 atmosphere is 760 torr. So 1.23 times 760 is the contribution of atmospheric pressure. Which is 934.8 torr. Okay. So what's the pressure of the sample of gas? Well, we had 24.3. Because we got this bearing down, we got this bearing down. And this is the only opposing force is the pressure inside that vessel against this much. 959 torr. So that easier answer. It helps to draw a picture. It's like we all know word problems are designed to confuse. I'm sorry. Oh, okay. Yeah, I don't think I'll buy any more of those little felt eraser things. I'll just buy a whole stack of these at Sam's Club. They work great. I think they were like, I bought a pack that thick, $15. So it'll be a while before I have to wash them. Are we good? All right. Okay, 29. Complete the following. Because real gas particles have attraction for one another. Which one of these is satisfied? Real gases act most ideally at standard temperature and pressure. On its face, A looks reasonable. Right? It's possible. B, we assume gas particles have negligible volume. Wait a minute. Because real gas particles have attraction for one another. Oh, yeah, E says at least two of the above are correct statements. So it could be those two. What does C say? 1 mole of an ideal gas at STP has a volume of 22.4. All right, that doesn't depend on real gases having attraction for one another. That's just a calculation from the formula. All right, so C is nothing special. As far as real gas particles have attraction for one another. Actually, B is not either. Right, that doesn't have anything to do with attraction. Negligible volume? No, that doesn't have anything to do with it. My mistake. D, real gases act more ideally at higher temperature and lower pressure. Now that is definitely true. Now, standard temperature and pressure is by comparison to 0K, standard temperature is high, compared to 100 atmospheres, 1 atmosphere is low pressure and high temperature. So we could make an argument for A and D being both correct, which would mean E would be correct. So I'd have to accept both D or E in that case. Right? If the question is written exactly like that. All right, let me see. We're going, oh. Yeah, we're talking thermodynamics now. Let me see how many questions we got. 60.
This is the fastest we've ever done study, yeah.
Really?
Yeah.
Oh, is that because we've gone over it before? Well, I thought I was kind of dragging my heels, stopping at each one and
We're already at 30 before 145.
oh. And I'm going one at a time, right? Yeah, I'm not skipping any. Well, let's see what these guys say. You'll probably remember the answer to these. If you have let's see, 30 through 33 is based upon that statement right up there. Right, and we're looking at what's true about the value of delta H first. 31 is Q and W, and the last one should be, yeah, internal energy. Okay, so let's look at this one up here, and I think this is a familiar situation. 1 liter bulb at STP that's connected to another bulb that's evacuated is opened. And what's true about these values? So, excuse me, we got this bulb that has standard temperature and pressure of a gas, and it's got a valve, and then we go to a vacuum. So we know what happens when we open the valve, right? The pressure equalizes and the gas distributes throughout. We're also told that the temperature doesn't change. So if the temperature doesn't change, then there's no transfer of heat at all. And if Q is equal to 0, then delta H has to be 0. Was there any work being done? It's not pushing against anything. It's just expanding gas in there. So there's no work being done. And delta E equals, right, Q plus W. Internal energy is, change in internal energy is the summation of what work was done and what heat was transferred. And since neither one of them was transferred, that's 0. So they're all 0. That would not be an efficient heat engine. You wouldn't want to try to run your car on that. You wouldn't get very far. All right, let's see. I don't want to just to squeeze too many questions into Thursday's class, because we're only going to have the short time period for that one. And we can bleed over into the lab if we need to today. What are we up to? 1:30? Yeah. So 15 more minutes and we'll be into lab time. So let's continue for a little while. 34. Choose the correct equation for the standard enthalpy of formation for CO, where the standard enthalpy of formation for CO is minus 110.5. Okay. If you're doing standard enthalpy of formation, you start with the product. And the product in this case is a gas, carbon monoxide. Then you work your way backwards. And you use the elements in their most stable standard states, carbon, right? And carbon in its most standard state is graphite. That's the most stable form of carbon. Oxygen is a gas, a diatomic gas is its most stable form. So we only need 1/2 of those. And then the heat of formation under standard conditions is a negative 110.5 kilojoules. That would be an expression of the standard heat of formation. Now, I don't know what the delta H for carbon dioxide would be, but if we did carbon dioxide, like, we'd still have carbon graphite. But then we have O2. That would be it. Right. One of these, one of those, next one of those. And whatever the heat of formation is, I don't know what it is. Let's see, 35. Did I give you your note? I gave you the notebook back. Yep. Nitric acid was first prepared 1,200 years ago by heating naturally occurring sodium nitrate, saltpeter, with sulfuric acid to produce sodium bisulfate. Sodium bisulfate is sodium hydrogen sulfate, and collecting the vapors of HNO3 produced. Okay, what's the delta H0 for that reaction? All right, if we've got our target reaction is sodium nitrate solid, we're going to have H2SO4, and that's going to produce sodium bisulfate, which is a solid, and HNO3 gas. And then we collect that, bubble it through water. Okay, That the alchemists did know several, what we call mineral acids. Mineral acids are those that have no carbon in them. They knew nitric acid, they knew hydrochloric acid, they knew sulfuric acid, and they knew various combinations of those. Nitric and hydrochloric acid in the right combination will even dissolve gold. That's called aqua regia, royal water. But back to the question. Calculate the delta H reaction for this one. All right, we have these heats of formation. So actually, this is really easy because the delta H for this reaction is the summation of the delta H's for the heated formation for the products minus the summation of the heats of formation for the reactants. Okay. And since, is this equation balanced first? One sodium, okay. One nitrate over here, and there's two hydrogens here, one there and one there, and a sulfate. Okay, we're balanced. So our coefficients are only one. So we multiply the values here by one, each one. All right, so let's see. Sodium bisulfate. What's its delta H? Sodium bisulfate is minus 1125.5. Minus 1125.5 kilojoules. And then sulfuric acid, H2SO4, minus 814 kilojoules. All right. Then we subtract, oops, sorry, wrong one. That needs to be nitric. This is bisulfate. Yes, this needs to be nitric. I'm getting them out of order. Minus 135. These have to be products. I get the products first. Now I go back to sodium nitrate, which is minus 467.8. Minus 67.8 kilojoules. And then sulfuric acid. Minus 814. 8. All right. So this one is 1125.5 and 135.1. That's a negative 126 0.6 kilojoules. And then this one minus whatever we get here, 467.8 and 814. These together minus 128, 1.8. Okay, so that becomes a positive. Right, get rid of that, just call that a positive. Add that to this negative. I should get 212. Right. Oops. No, sorry. Move my decimal too far. 21.2 kilojoules. That's positive. So what does that tell us about this reaction? Got to put energy in. It absorbs energy from the environment. So when they put these two together, maybe it said so. They heated them, naturally occurring substances. Well, it doesn't say, but you'd have to add some heat. You'd have to get some heat from somewhere. Either the solution would get cold, drawing heat from its surroundings. The containers would get cold, or you'd have to put a fire under it. All right. Force between two bodies having identical electric charges. 36. This is definition. If you've got two bodies that have the same charge, like positive, positive, what's that going to do? The force they're going to feel is repulsion. Or if they're two negatives, they're also going to be repelled. That was part of the controversy for how the atom was built up. Because once it was established that the nucleus of the atom was packed with protons, all positive charge, and neutrons, they had to explain, why didn't it just fly apart, right, with all those positive charges in there? So they came up with a solution, and actually eventually it was measured. The strong nuclear charge was holding them together. Once you get these particles close enough together, then the strong nuclear charge takes over, and it's much, much, much greater than the electrostatic repulsions. There's also a theory that wasn't mentioned in this talk, that that's what the neutrons are there for. There's an exchange of particles. So inside the nucleus, this nucleus can send an electron over to that proton and make a neutron, and it becomes a proton. So it makes a neutral particle out of itself, and now it becomes positive. So, and there's some evidence to support that, because the bigger the nucleus, the higher the ratio of neutrons to protons. When you first start off, you've got roughly, like oxygen has 8 protons and roughly 8 neutrons. But when you get down to, say, selenium, bigger atom, 34 and 34 is 68. It's got more neutrons than it does protons. And it continues to increase the number of neutrons. And it takes that many neutrons to hold the nucleus together. And even then, it's not entirely successful, because uranium-235 is unstable. It splits apart on its own. And let me see. How many does that leave us? I used up 36. 36 and go to, and that took us one lecture class period. Let me look at the nature of these other questions, because they may take a little longer to.
Yeah, because we're trying to get into like the math part, the mathematical part.
Yeah. Maybe we better dig a little bit deeper, move a little bit further, so we'll have enough time Thursday to finish up. I'm sorry.
We go to the bullets. That was just 15 questions.
Oh, maybe that's why I left it blue as an indicator. We're on 37. Okay. 37. Which of the following molecules has no dipole moment? Okay, how we answer this one. If we're talking about the whole molecule, we need to know polarity of the bonds and the geometry. So, and we've got just 3 and then all or none. Oh. So we're looking for no dipole. Okay, so we're starting with carbon dioxide, and we're going to ammonia and water. Now, if you're given something that you're not familiar with, you haven't done before, then you would add up all the valence electrons, and then you would form your, let's see, carbon would have 4, and then 2 times 6 is 12. That'd be 16. Yeah. And you would form your bonds here like that. So that'd be -4 would be equal to 12. There's 2, 4, 6, 8, 10, 12. And then you make your octets. And so we would take these 2 here, and those 2 there. Now you have your Lewis structure And we've got a carbon with only two groups, which is linear. And even though dipole is like this and like this, it's opposite and equal in magnitude. So that means this is nonpolar. Right? No dipole. That's a good one right there. And if we did the same thing with ammonia, we'd end up with that one with hydrogen in the back, hydrogen here, here, and here, forms the triangular base. And then the tetrahedron would have the lone pair up here. So this has a dipole that direction. So that's a dipole. It doesn't work. Water, we know water. We've done water so many times. It's dipoles like that. All right, so the only one with no dipole is carbon dioxide. Now, while we're here, what's the hybridization on that carbon? Remember, when you have two groups and it's linear, you have an sp hybrid. So the carbon is sp hybridized, and that gives it two p orbitals that are unused. One of them makes a pi bond with this side, and the other makes a pi bond with that side. Okay.
You said the two P's are impaired, right?
2p is linear. Right. Was that the question? Say it again.
You said the two P was unpaired because it left two P orbitals unpaired, right?
Yes, these two, right. They did not enter into the hybridization.
Got it.
They're free as atomic orbitals. And they overlap with p orbitals on oxygen. Now, oxygen is going to be, well, if you just look at one side, oxygen here has there, and there. So we have 1, 2, 3 groups here. This is sp2 hybridized with only one p orbital available. And this p orbital overlaps with one of these p's. That forms a pi bond there. And then the other side has unused p orbitals like this. We draw them kind of angular. And those form the other pi bond on the other side.
Okay.
So it takes two unused p orbitals from carbon, one each from the oxygens to complete the structure. And the reason we have to do that hybridization is because the theory doesn't allow us, the atomic orbitals arrangements don't allow us irregular structures. Right? The perfect example is methane. Right? Carbon is 1s2, 2s2, 2p2. Right? So you've got 2 electrons in the s orbital, 2 electrons in the p orbitals, valence orbitals. And you don't get a regular tetrahedral shape out of that. We had to hybridize in order to make it work. Let's see, 38. I lost my place. Choose the molecule with the strongest bond. All right. Seems like just yesterday we talked about this one. All these are halogens. Okay. The strength of the bond is based upon a couple of things. One is the overlap of the orbitals. The iodine is huge, and the overlap is incomplete. It's a small overlap, which gives you a weak bond. As you get, and we're using, let's see, iodine would be using 1, 2, 3, 4, 5. Be using 5 P's. This will be using 4 P's. So you're getting smaller and closer to the nucleus. And the closer you can get the nuclei together, then the more overlap you can get in those orbitals. And this one is overlap 3p. When you get down to 2p, now you've got another issue. Because you've got 9 protons in each fluorine. Right? And they're going to be pushing against each other. When you get close enough to them that these positive charges start to electrostatic interact, they will weaken the bond. They will start to push against each other. So even though you've got orbital overlap, you still got those nuclei pushing against each other. That's why your maximum bond strength is right there and not here. All right, 39. In the gaseous phase, which of the following diatomic molecules would be the most polar? All right. So what we're looking for is the one where the elements are furthest apart on the periodic table. Right. If we can find that one, if that was in the group, right, cesium's in the lower left, fluorine's in the upper right, that bonding should be the most polar. Well, there it is. Cesium fluoride. That's the most polar bond in all that group because of the difference in electronegativities. And about 40. All right. We got these 3 molecules. And let's see. Roman numeral 1, 2, and 3. I'm just going to draw the structures. Got this one. Let's get 2. It's right here. And oops. Nope, wrong place. There and there. And then the third one. Here. Remember, everywhere these lines meet is carbon. And then for every carbon, you got 4 bonds. So this carbon has 1, 2, 3 bonds already. That means we fill in the missing one with a hydrogen. That's organic chemistry convention. So whenever you got one like this, 1, 2 on that carbon, that means you got 2 hydrogens here. And you can see that in the formula. Okay, now the question is, which one of these has equivalent carbon-carbon bonds throughout the molecule? Well, obviously here, you don't have. That's a single, 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 and a double. So those are different bonds. These singles are similar. These singles are similar, and those doubles are similar. Or you might get delocalization of electron density to go like that. So these 3 might be similar. But for this one, all of those bonds are the same. Exactly the same strength and length. That's why this structure is very stable. It's the lowest energy. And it's lowest energy because electron density is delocalized over the entire molecule. And that's kind of like the lead into molecular orbitals. Because the molecular orbital is based upon the whole molecule, not individual atoms. And delocalization is the key. All right, 41. Okay, electron configuration of a particular diatomic species is, let's say, 2s superstar 2s. Let's see, this is no mixing. Sigma 2p pi 2p pi star 2p. So as far as we need to go. Yep. So we got 2, 2, 2, 4, and 2. 2, 2, 2, 4, 2. Now what's the question? What's the bond order for this species? All right. 2, 4, 8 minus 2, 4 divided by 2. So that's 4 divided by 2. Bond order of 2. Let's see. We've still got room on this one for more electrons, don't we? Right. What if we turn that, let's just say, whatever it is, neutral now? What if we added an electron to it? Where would it go? Go right here. Right. That means this would be 5. And this would be 1.5. We would decrease the bond strength by adding one to this one. Or if we went like that, it'd be the other way around. We'd be subtracting one of those two. Right? And that would increase the bond order to 2.5. Actually, in this case, if we went to 2 plus, right, then we'd go all the way up to 3. Because we're taking electrons away from anti-bonding orbital, strengthening the bond order. All right, that was 41. Let's see. 42. Let's see. What's the hybridization on each one of these? Okay. All right, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 5 carbons. This one has 2 hydrogens. I'm going to draw the hydrogens in the way we would see them, like that, rather than H2. Draw them in like that. This one would have a hydrogen there. This one would have oxygen there. This one had 2 hydrogens. And the last one has a nitrogen on it. Okay. I'm going to draw in all the missing lone pairs too. 2, 4, 6, 8. Let's see. I'm missing a double bond. Here we go. Right there. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And this one, 2, 4, 6, 8. There's all your lone pairs. Okay. As far as the carbons go, this is that carbon is sp2. 1, 2, 3. 1, 2, 3. This one's 1, 2, 3. sp2. This one's sp2. Right. Three groups around the carbon. 4 around this one is sp3. And 2 around that one is sp. Okay. How about nitrogen while we're here? Right. 2 groups around that one. That one's sp. How about this one? 1, 2, 3, sp2. You don't hybridize hydrogen, right? It just is. So that would be, A would be the answer to the question, and I just added some extra information. See any blue yet? 43. Which of the following statements describes the Heisenberg uncertainty principle? Heisenberg was part of that series I've been watching. He was on one side. He was the rebel side, and he and several others. And Einstein and a bunch of his colleagues were on the conservative side. Heisenberg and his colleagues approached the behavior of subatomic particles from a statistical, mathematical standpoint. And if I can remember the quote correctly, Einstein was quoted as saying, God doesn't play dice with nature, or something like that. He says he's definite. But as it turns out, uncertainty the statistical approach was the only way to solve the problem. So Heisenberg said what? That if you measure on the subatomic level, if you measure the position of a particle, you can't know how fast it's going. In other words, you know nothing about its energy. If you can measure how fast it's going and estimate its energy, you don't know where it is. Okay. So which one works for that? A, it's impossible to accurately know both the exact location and the momentum. The momentum of a particle is, that's the Greek letter rho, is equal to the mass times the velocity. And if you're talking about an electron, the mass is not going to change. So we're really talking about the velocity. All right. Mendeleev. Remember what he was famous for? This thing right behind me. Now, why is he given most of the credit for the concept of the periodic table? He wasn't the only one working on the periodic table.
Isn't it, 'cause he's the one that left the blank spaces because new ones would be
Uh-huh.
discovered?
Yeah, he left blank spaces based upon physical and chemical properties. And the elements weren't known yet. And he didn't want to put something in that space just because it was in the right order. It would be out of character of the group. So he left the space and he predicted the properties of the element that would be found and placed in that position. And every one of them was eventually found. So he gets credit. And that would be C. Emphasize the predictive properties of the periodic table. Okay, there's the blue. All right, so we'll pick it up with the blue on Thursday.